Hello. In the last session, we have discussed about one phenomena called as the gyroscopic effect. So we have understood that in gyroscopic effect, if in a system there is a body which is rotating about an axis, we are calling that as the spin axis, and that axis of spin is getting rotated about another axis which is perpendicular to it, or maybe a torque or a moment is applied on this axis such that the spin axis is trying to turn about an axis perpendicular to the spin axis, then the entire system as a whole rotates about a third mutually perpendicular axis. That is called as the gyroscopic effect, or we are saying that the body will start precessing about a third mutually perpendicular axis. So we have seen this example. So say there is this disc, say, which is rotating about this axis. So we are calling this axis as the spin axis, and say a moment is getting applied on this axis such that now on this plane this tries to rotate in this fashion. So that means the axis or the axis of spin is maybe getting turned or has a tendency to turn about this z axis which is perpendicular to the board. Then this entire body will start precessing about a third mutually perpendicular axis which is the z axis. So y becomes the axis of precision here, and z is the axis of applied couple. So this effect as a whole is called as gyroscopic effect. Now we have again talked about two terms, that is natural precision and forced precision condition. Now while understanding this, we have understood that there will be this couple which is getting applied, and we have as well determined its magnitude, this gyroscopic couple, to be equal to I omega p, where let us say whatever this disc is having some mass m and which is rotating at some angular velocity omega. So this I omega is the speed at which the body is spinning. So I can say that, or I'll say that omega is the spin velocity, and omega p is the velocity by which this body is precessing. So this is precessing velocity, right? So we get the magnitude of the couple to be as product of this I omega is the angular momentum of the disc, and omega p is the precision velocity, that means by which velocity the body starts precessing. So this is the magnitude, this will be the magnitude of the gyroscopic couple, right? Now we are talking about two terms, one or two conditions rather. One is the natural precision condition and one is the forced precision condition. Now let us first try to understand the precision, right? Now let us see this as the arrangement, that there is this disc which is rotating about this shaft. So this shaft is the spin axis, right? Now this is supported by two supports. Now let us say by any chance one of the supports support is breaks, right, or it is removed. So what will be the tendency of this shaft? The mass of this body will be acting from this point, right? So this force or the weight into this distance, it will create this moment. So for this, as if this is going to fall down. So that means here, when this disc is rotating at a very high velocity and now the support is removed, so it will try to fall down. So instead of, so one torque or a moment or a couple is getting applied from this point over this pivot point. So instead of falling down, this entire system will be start rotating about the third mutually perpendicular axis. See, so this spin axis is the x-axis. Now perpendicular to the board or the camera right now, I can say, is the axis about which this is having a tendency to rotate. But instead of falling down, it will start rotating about the third mutually perpendicular axis, which is y-axis. Now this condition or this effect is basically called as the gyroscopic effect. Now if when or the condition, if you say, when the support is removed, now according to the applied torque, for the compensation, the body will start moving around the y-axis, right? So when it is moving, so we cannot say by which velocity it is going to precess. Now if I want to determine that, then I know what is the couple, so it will be mg into this r value, which will be equal to this value. Omega is known to me. If I know the mass, I know I is mk square. Mass into the radius of gyration square, I get mass moment of inertia. Omega is known to me and I can determine what is omega p. That means I am determining omega p, right? So the conditions where I see that the gyroscopic couple, or instead, now I will not call it to be as gyroscopic couple, rather I will call it, if the applied torque or the couple or the moment, if this is known or which can be determined with the given conditions of the system, if this is known and omega p is unknown for that matter, or what we are trying to do, it is unknown or to be determined for a system, then this situation will be a natural precision condition, right? I hope you have followed. So when this applied torque or the couple is known to me and the omega p is unknown in this case, this mathematically, if you want to deduce or determine, want to understand whether it is a natural precision condition or a forced precision condition, then I will think it in this way. So if this is known and I have to determine omega p, then it is a natural precision condition. Now second can be, now instead of both the supports are intact, now this body is rotating, spinning with omega, and I forcefully turn. So I am turning this, or this entire system turns with some omega p. That means when omega p is known, so when omega p is known and I am determining what is the couple, then we call it as a, so when omega p is known, that means the precision velocity is known, and we have to determine, and this gyroscopic couple, this v is unknown, or when it is to be determined in the problem or in the situation, then this condition is the forced precision condition or a forced precision system. This is how we can even identify. So looking into the system, we'll try to understand whether I know the precision velocity or the velocity of the spin axis, by what velocity is turning. If it is known to me, then definitely I'll be assured that this is a forced precision condition, and I'll have to determine the couple value or the gyroscopic couple value. Or if I see in a given situation that omega p is not known to me, but I can deduce what will be the applied, or what is the applied torque or moment in the system, then in that case it will be a natural precision condition. Now it's obvious that this couple, when we say couple, it will have magnitude and certainly it will have direction. Now this is vector quantity, this is a vector quantity, so obviously a couple will be a vector quantity because it will have magnitude, as well as definitely when we are saying couple, so it will be having a sense of rotation or sense of application, so it might get applied clockwise or counterclockwise. So just by finding out the magnitude will not give me the solution, or it will be an incomplete solution. I will have to as well determine the sense of rotation also for the couple. So here now we will try to understand or how we can determine the direction of this vector. So I will take the same example, say this is rotating. So, and for understanding we will take the condition as forced precision. So what we are trying to understand here through this is how I can determine the direction of vector. So here we are trying to understand the direction of the vector. Now let us say, given that, so we'll have to understand through the given condition, say if it is given to me, what is given to me when we are saying forced precision, that means omega p will be known to me. So I know what is the spin velocity omega, this is known to me. Omega known to me, that means the sense of rotation as well is known to me, magnitude is also known to me. Omega p, that is precision velocity, is known to me, that means again the magnitude of omega p is known to me, as well as the sense of rotation of the precision velocity is known to me. So complete vector is known to me. So these two things are known to me. What I need to determine is the couple. So we know the expression. So we know the expression that gyroscopic couple is equal to I omega and omega p. So mass is known to me. We know that I is equal to, right? So now the unit for this is Newton meter. So gyroscopic couple magnitude is known to me. Now what I am fighting for is to determine its direction, how this couple is getting applied, whether it is clockwise or counterclockwise. So let us take the same example here, right? And so from the given condition, if it is, the given condition is that the disc is rotating clockwise. So this is the left side and this is the right side. This is very important because we have to as well judge the direction of this vector, right? So let us say the observer is standing to the right. So this is the observer who is standing to the right and he is looking at the system and it is rotating clockwise. So as well as when the observer is looking at this system from the top, this y-axis I have taken as the precision axis, right? So when he is looking at it from the top, let us say the system is turning clockwise. So system is turning clockwise. So these two things are known. As I have said, omega is known, omega p is known. So that means that sense for both the conditions of the observer, it is known. So again, I can just replicate the system situation like this. So I am standing to its right and I see that the disk is rotating clockwise. And when I look at it from the top, I see that, so clockwise will be this, that means moving to the right. So the entire system is turning in this fashion, right? So we will take the spin axis as the x-axis. Spin axis is the x-axis and the precision axis is the y-axis, as I have marked, and the applied torque axis is the z-axis. So about the z-axis, that means for our condition, again let us make it out, x-axis is the spin axis, that means axis of the shaft, y-axis about which precision is taking place. So the third mutually perpendicular axis will be perpendicular to the board. So the torque will be getting applied in this fashion, whether clockwise or counterclockwise, that we will try to understand with this vector diagram. So we'll try to understand this vector diagram. So this is the y-axis I am showing. This is the z-axis, the x-axis, which is axis of spin, and this is the z-axis. So this is x, y, and z. So now we will apply the right hand screw rule. To understand or to get the direction of the vector, right? So what does the right hand thumb rule suggest? So when the fingers are curled in the clockwise sense, the thumb will be pointing outwards from my direction of vision. So observer is standing here. If this is the condition, the thumb will be pointing outward, which will be the direction of the vector, and the fingers which are getting curled in the clockwise sense from my point of view, they are turning clockwise, so vector will be pointing out from the pole of the vector diagram. So this is, and we are trying to understand the vector diagram, and say this is the pole of the vector diagram, I name it as a pole. So if I look at this system, I am standing here and this is how the system is. So when I look at it, it is turning clockwise. So I will use my right hand to apply the right hand screw rule or thumb rule. So my fingers should match with the rotation of the spin, so which is clockwise. In that case, the vector will be pointing out from the pole. So whatever that magnitude is of omega, this vector looking from here, observer is here, mind you. So observer is here and he is looking at the object. So vector will be pointing outward and it is turning clockwise. So this vector is the spin vector, right? So this vector is the spin vector. Now let us talk about the precision vector. So when I am looking at it from the right, it is turning clockwise, so I got the vector to be as this. So now for precision, I will have a look at it from the top, and let us say it is given condition is that the precision is, which is known to me, is clockwise, so it is turning in this direction. So when I am looking at it from the top, it is turning clockwise, so that means the vector will be pointed downwards from my point of view or the observer's point of view. So that means the vector will be pointed downwards, which is due to clockwise rotation. And for this condition, the observer, what is the location of the observer? The observer is looking at it from the top. The observer is looking at the system from the top and it is turning clockwise. So I get this vector to be, so this vector is the precession vector. Now comes the time where we will determine the direction of the couple vector. Magnitude of couple is known to me. Now, the simplest way of determining this couple is by turning the spin vector, in the direction of the precision by 90 degrees. So how we are getting the so how will be getting so we want to determine the gyrocouple vector how we are getting it. We will rotate the spin vector in the direction of precession by 90 degrees. That will give me the couple vector or the gyrocouple vector. So what we have to do, rotate the spin vector in the direction or in the sense of precision by 90 degrees. That means I'll have to shift the spin vector onto the z axis, right? So I will just, as if I'll hold the tip of the spin vector, and how is precision? Precision is clockwise. That means this is supposed to move to the right? So I will hold the tip of this vector and rotate it in the precision which is clockwise by 90 degrees so that it meets the z axis. So when it is rotated here by 90 degrees, I get this vector as the gyroscopic couple vector. Now I'll call this as active gyrocouple. Now, to determine its sense of rotation, now we have considered the observer to be here, then to the top, then according to the first angle method of drawing, if you say, in the first, if you are considering that entire system in the first quadrant, then the third position of the observer will be here. So one is from the right, then looking at it from the top, and then looking at it from the front, because the motion will be on this, or this couple will be getting applied on the plane XY, that is about Z axis, right? So if the observer is standing here and he is looking at the vector, I see that the vector is getting pointed outwards. So I use my right hand according to right hand screw rule. Here I will match my thumb with the vector. I see that my fingers are getting curled by clockwise sense. That means the application of this gyroscopic couple is coming out to be clockwise from the observer's point of view. Now, if the observer is standing here for that matter, in that case when the observer will look at the vector, so then me as an observer, I'll match my thumb with the vector. So it is, this arrow is pointed towards me as an observer. So I'll point my thumb towards me of the right hand and I see that the fingers are getting curled counterclockwise. So from this point of view, I'll say that it is turning counterclockwise. But the position or the location of the vector is not going to change at all. Fine. So why? Then I am calling this as active gyroscopic couple. Now, if there is active couple, that means there has to be reactive couple, right? So that means what is happening in this case is, so when now you as an observer, if you are looking at it, it matches with the position of the observer standing here. So when it is turning clockwise, it is said that according to your point of view, it is turning clockwise. For me, I am standing opposite to the system. For me, it will be counterclockwise, right? So now when this couple is getting acted upon from this, that means from the viewer's point of view, those who are watching the video, from the viewer's point of view, the rotation should be clockwise, right? So that means when the body is precessing, this entire system is subjected by a couple which is clockwise, and this entire system is held by the bearings. So if this system is trying to turn clockwise, the bearings or the frame of this system will try to hold it back, right? And to stabilize it, this will be the reactive couple. So that means, and it will be exactly opposite to the active couple. So in that case, now we'll see that exactly opposite to me, opposite to the gyroscopic couple, then this couple which I am showing it with blue, this will be called as the reactive gyroscopic couple, and according to this given system, this will be counterclockwise. So that means this is the action and this will be the reaction. So if it is a say the rotor of an engine which is mounted on the frame or the chassis of a vehicle, and when the vehicle is turning, so what will happen, that gyroscopic couple is getting applied in the system, so it is trying to turn clockwise, but the frame is trying to keep it or move it counterclockwise, right? Now if the speed values are too much high, then the magnitude of this couple will be too high, and maybe you will see that due to this reaction the body topples. So that is how that is the, or maybe in that case it will try to just pull out one bearing from one side of the bearing, or it will try to impress the other side of the bearing. So when the turn is opposite, then maybe the direction of the couple gets changed. So in that case again this alter. Now this is happening only when the system is turned. There is a precision velocity. If this is steady, the spin axis is not turning at all in any condition, then gyroscopic couple will not be in the system, right? Only when this is getting turned, or maybe one of the supports is loosened or maybe gets removed, then things will be subjected to this effect. Now we have tried to understand, when the precision is known to me, what will be the action of the couple, right? Now this can get altered. There can be a system where I want to determine or predict if something happens to one of the supports, then in which direction this system is going to precess. So that also, so this is the logic. So how we are determining it? When we are knowing these two vectors, that means vector of precision and vector of the spin, when these two are known to me, I am applying this fundamental of right hand screw rule, and so what we are doing, we are rotating the spin vector in the sense of precision by 90 degree. So if I want to determine the active couple, when the active couple is known to me and I want to determine precision, I just do the reverse of it. Now the gyroscopic effect will be this only. If moment is getting applied, the body will precess. If I precess the body, it will be subjected to, or it will experience a couple. Right? So let us say that now it is a natural precision condition. So maybe again we take the same example. It is, so there is a disc, say this is a disc and it is supported by bearings.